Welcome to lesson 5.3 on solving trigonometric equations. Now this is going to take our skills from 5.1 and 5.2, dealing with just those expressions, and we're going to kind of throw that together with our knowledge of quadratic and solving polynomials, and we're going to find ways to solve these trigonometric equations. So let's take a little look at one. So starting off, we have a little tiny equation, 2 times the sine of x equals 1. Now, ideally, as we're working through this, we want to know what x is, but sometimes it's a lot easier to solve for that function before solving for that variable. So we're going to isolate sine of x. When we do that, we have to divide that 2 over. So we get the sine of x is equal to 1/2. Now, this should look familiar to us. We've seen sine of theta or sine of x equal to 1/2 a ton of times, starting from the very beginning of chapter 4. And well, what does this mean? This means we want the x values, which are going to give us a sine of 1/2. Now, we do have kind of the graph of a sine curve right here. What we're going to be using for the most part, at least for this first half of 5.3, is the unit circle. So we're pulling those unit circles back out. We're going to be using those a ton in this 5.3. So sine is 1/2. Where is sine equal to 1/2? Well, we know that happens over here at pi over 6. And then if sine is positive, we know it has to happen on the top half plane. It happens also over here at 5 pi over 6. So if I were to just look from 0 to 2 pi, just one rotation, I have, well, 2 answers to this, right? It could be pi over 6 or 5 pi over 6. However, we're not always going to be working from, say, 0 to 2 pi, aka just one rotation. For the most part, we're going to be working kind of infinitely. So let's take a look at what that looks like as we look at this sine graph right here. That's just a representation of it from the unit circle. Well, at 5 pi over 6, which is right here, we know it's one of our solutions. And at pi over 6, right here, we know we have another solution. So let's start at that pi over 6 real fast. If I wasn't just limited from 0 to 2 pi, and I could go to 4 pi or negative 20 pi, or I could use any of those rotations, as we know with all our trig functions, after one full rotation, as we end up at that same terminal side, our trig value doesn't actually change. So if we take pi over 6 and add a full period, that 2 pi, that's going to land us at another one of our possible answers to this equation. So from pi over 6, if you add 2 pi, you're going to get, well, another answer. Equally, if we were at that 5 pi over 6, right, and we add one full rotation to it, we end up on that same terminal side. The sine is still going to be 1/2 after that whole period shift. Now we know this doesn't just happen in the forward direction. If these were to be negative angles as well, we would find that 5 pi over 6, if you removed 2 pi, you get another answer. Or if you're at that just pi over 6 and you remove 2 pi, you would keep getting more answers, right? Technically different angles, but they're all just a difference of 2 pi, either forward or backwards. Now, if we were to continue this forever, right, even off the page, think about how many different solutions we're going to get. So right off the bat on the unit circle, we only had 2 of them from our basic unit circle from 0 to 2 pi. But if we allow the option for any range of that, we're going to really have infinite solutions. And to do this, to represent this, we're not going to write that out forever, right? That's just going to be one problem we'll spend the rest of our lives on. We're going to use some shorthand, some new math notation. So if you notice from pi over 6 over here, when we add 2 pi, you take that original angle from the unit circle and you add 2 pi. Now, if you did that again, you'd be at 4 pi, do it again, 6, 8, 10, right? So we're adding multiples of 2 pi. So we take that original angle from our unit circle, and to represent the answer that kind of encompasses all answers of it, we're going to add that 2 pi, but we're going to have n multiples of it. So that means we could have positive n, or say n could be positive 3, it could be negative 10. It's going to take the representation of every single one of these that's shifted by 2 pi. And similarly, with our 5 pi over 6, our other original answer from that unit circle, we want to make sure we include every other iteration of this. And to do that, we're just going to either add or subtract. Conventionally for us, we're going to add 2 pi, and then we're going to have n multiples of that. So 2 pi n. So every time we solve these, no matter the order we're going to be going with, we're going to always start with the unit circle for the first half of 5.3. And then we're going to extrapolate that kind of into the infinite. So we're going to have to make sure we have every answer included on that. We'll see what happens when we kind of throw a limit on it. Now, where every problem is going to have that in common for the most part, as we go through this, you're going to see there's going to be a few different techniques of how we kind of get to this point of solving that equation. So let's take a look at a few. So looking at number 1, for number 1 and number 2, and for this first page, I'm going to have you guys pause at the end of it and give these evens a shot. So I'll give those a little star for you guys. We'll be giving these evens a shot in a second. So for number 1 and 2, our hint is to solve it by collecting like terms. Well, what does that mean? Well, we have a sign on the left, a sign on the right. Just if we had just an x on the left and right, we would combine like terms, right? We'd move that variable over. We're doing the same thing where we move that whole function over. So I'm going to add the sign of x to over here to the left, and we're always going to get every function onto one side, and then all the numerical values onto the other. So you have 2 sine of x minus that root 2 equals 0. And now I'm going to add that root 2 and then divide by 2. So that function sine by itself is just root 2 over 2. So here's where that unit circle comes in, where in 4.7 we jump straight to inverses now. We'd have that tool set. We're going to get there eventually. So we're going to kind of treat it like the beginning half of chapter 4, where we're going to be using that unit circle as a reference. So hopefully you'll pull out your unit circle, and you'll look at your unit circle and ask yourselves the question, for what angles do we get that sine is a root 2 over 2? Well, we know that has to be positive. We know the first one of those happens at that 45 degrees, or for us, because it's in radians, pi over 4. And then it gets reflected to quadrant 2 because it has to be a positive sign over here at 3 pi over 4. Straighten that out a little bit. So these are our 2 possibilities from 0 to 2 pi, aka just one rotation of that unit circle. But as I saw above, I'm not limited to just the unit circle. I want to solve this for every single possible x. So, well, what do? We're going to be adding those multiples of 2 pi. So again, from pi over 4, we're going to add 2 pi n. That's one possibility. Or from our 3 pi over 4, we're going to be doing the very similar thing where you start with that 3 pi over 4, and then you add that 2 pi n, and that's going to give us every single possible outcome. So similarly in a bit, for number 2, you'll do something the same way. You'll combine all those cosines, and then when you get that cosine of x solved for, you'll be relating back to that unit circle. But for now, we're going to keep moving. So looking at number 3, it's going to be asking us to extract square roots. And the difference between number 1 and number 3 is now our function is squared. So if our function is squared and by itself, This you can kind of imagine solving as if you had, say, 4x squared minus 3 equals 0. And how you'd approach that, we're doing the same thing here, it's just that x for us now is sine of x. So we're going to add that 3 over and divide by 4. So sine squared of x is going to be 3 over 4. And our known values aren't sine squared, right? Not cosine squared. It's always sine of x, cosine of x. Those are those known values we've worked with on that unit circle for so long. Well, how do we do that? Well, we do that by taking the square root. So here I'm going to take the square root on both sides, so I get that sine of x isolated by itself. So it's going to give me a square root of 3 over, not a square root of 4. We can write that as a 2, right? Square root of 4 is 2. And then there's one tiny detail. See if any of you catch it. Yeah, the positive and negative, right? Because we took that square root. We have to include the positive and the negative for our answers. So I want to know now, where's sine of x going to be root 3 over 2 or negative root 3 over 2? So again, you guys will have your unit circle. You'll pull your unit circle out and you'll go, okay, so where am I having a sign as either a positive or a negative? Root 3 over 2. And a really easy way to do this is if you find it in quadrant 1, which happens at pi over 3, you can just reflect it into quadrant 2 for sign to stay negative. And that ends up at 2 pi over 3. And then both of these can be reflected down to give the negative counterparts. So once you find it once, it's easy to kind of find those other three. And this one's going to be 4 pi over 3 and 5 pi over 3. So, kind of as expected, instead of having two possibilities, because say just sign being positive, we're looking at positive and negative. So we have 4 different options. Now here's something nice with this type of answer that you can kind of streamline the work you have to do for writing it out. So if we look at number 1, both of these angles were unique, right? So we just had to keep adding 2 pi, adding 2 pi, adding 2 pi. And now we could do that on number 3. I could do pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n, right? And etc. However, because you can hopefully see something happening between pi over 3 and 4 pi over 3, and then equally from 2 pi over 3 to 5 pi over 3, these are exactly not 2 pi, but pi apart from each other. So from our first angle to this one is a pi distance, right? And if I go one more pi, I end up back where I start. Now, if I keep doing this over and over and over in the positive or negative direction, I really only need this first angle. Instead of adding 2 pi multiples, I'm just going to be adding a pi multiple at a time, and that'll help encompass this other angle. Now, the nice thing, it's not just happening from pi over 3 to 4 pi over 3, but also with our other 2 angles. So instead of having to write out 4 different variations, we're actually only going to have 2 on this one. The first being from pi over 3, and now I'm not adding 2 pi, because I can just do half of it, because I know that value. So pi n, there's one of my angles, and that's going to encompass both of these. Or from 2 pi over 3, an extremely similar thing. X will be equal to 2 pi over 3 plus pi n. So this is why it's nice, even if you have the unit circle, to kind of even sketch it out. If you start to see that things are a distance of pi or pi over 2, some nice known value, rather than you having to hunt down what that difference is, because it would change, right, each time for number 1, but for these it'd be even. If you can recognize it, then you can change this to shorthand. Now you can absolutely write all 4 of those out separately. However, this is going to be the more ideal form to see and recognize that change. Now again, when you do number 4 in a minute, you're going to have something similar. solve for that cosine squared, and then take the square root of both sides, and then you'll build your answers from there. Now, lastly on this first page, we have the skill of factoring, and we saw a bunch of this in 5.1 and 5.2, and it's not going to go away. A lot of the things we see with trig stuff, we can relate to our skill sets of polynomials, specifically quadratics. So all the factoring in quadratics, difference of squares that we worked with already, we can use those skills in solving these trig equations. Well, how do we do that? Looking at number 5, we can't factor anything yet because they're on opposite sides, but just like if we were to write this, say, as a typical quadratic, we would typically bring everything onto one side, right? And then solve from there, or then factor from there. We're going to do the same exact thing when we're working with trig. So I'm going to bring this 2 sine of x over to that left-hand side. So now on that left-hand side, I see that there's 2 terms, both with a sine of x, so that's where I get my factoring happen. And this factoring move, oops, that should be a 2, should feel really familiar to what we were doing in 5.1 and 5.2. So again, just as if it was a quadratic, when you break it up with multiplication, we can then set each of those equal to 0. So we have sine of x equals 0, or sine of x minus 2 equals 0. So sine of x equals 0 is done. We'll work that in a second. And then we have sine of x minus 2, so I'm just going to solve for sine of x. So we're going to be looking at the unit circle. Where is sine giving us 0? And then where is sine giving us a 2? So I'll get a little unit circle sketched out for us. See if we've got any shorthand stuff we can do, like number 3, to write a little bit less out. So sine is 0, where cosine is 1, right? Those opposites. So I know cosine is 1 over here, well, at 0, or 2 pi, or 4 pi, right? And then it's the same value again over here at pi. So just off sine of x equaling 0, I'm seeing once again, kind of like number 3, I could start at 0 and add multiples of 2 pi. I could start at pi and add multiples of 2 pi. But because these are nice and they're exactly pi away from each other, and then once again, pi away from each other, I can really just start at 0 and add multiples of pi n. Well, 0 plus pi n, that's just pi n. So one answer to this equation is any multiple of pi, any integer multiple of it, so positive 3, negative 20 of pi will make this statement true. So that handles sine of x equaling 0. Now take a moment, look at your unit circle, find where sine of x is equal to 2. And hopefully some of you are kind of confused or already caught it. It's called the unit circle for a reason, because it's 1 unit out as its radius. So sine of x equaling 2 can't happen, right? The largest it can be is up at 1. So this piece of it does not exist, which leaves our answers as just pi n. So again, we covered factoring for number 5, using square roots from number 3, and then combining like terms, collecting like terms to number 1. You're going to be kind of mirroring these skills, so give it a pause, give it a second, and work out number 2, 4, and 6. And when you come back, we'll have them done. So hopefully you paused and gave those evens a shot on that first page. So we're going to go over them and write that final answer together. For some of them, there's going to be some nice little shortcuts like our first 3, and for others, are going to be stuck kind of writing each one individually. So looking at number 2, all I'm doing is I add the cosine to the left. I'm then solving for cosine. So get rid of all those coefficients and those constants, I end up with where is cosine of x? Root 3 over 2. We know that happens at pi over 6 and 11 pi over 6. Now the issue, similar to kind of number 1, is it's not some set distance between these two angles. So there's no shortcut to kind of write both of them in one answer. So we got to start with that pi over 6. We're going to add those full multiples of 2 pi, and we'll do the same for 11 pi over 6. So we have x is either 11 pi over 6 and every 2 pi multiple, or 11 pi over 6 plus all those 2 pi multiples. So for number 2, no shortcuts. Number 4. So for number 4, we're using square roots. So we're going to add the 1, divide by 2, and then take the square root. Now, you might have an extra step in here where you did that rationalizing, because we don't want just 1 over square root 2. We want to rationalize it. And when we do, we're going to find where is cosine of x positive and negative root 2 over 2. Well, hopefully, whether unit circle or not, you're recognizing that root 2 over 2 always correlated with that 45 degrees or that pi over 4. Now, when it comes to writing the final answer for this one, we could write all 4 of these like up here and add every multiple. However, let's take a little bit of a closer look. So like number 3, from pi over 3 to 4 pi over 3, it was pi away and then pi away again. And we have that same thing happening right here. So from pi over 4 to 5 pi over 4, it is pi away, and you go pi again, you end up in the same spot, and you could do that forward and backwards. So we could write pi over 4 plus pi n, and then 3 pi over 4 has that same thing happening as well. However, there's something we do know about pi over 4 and 3 pi over 4, and then 3 pi to 5 pi over 4, and then 5 pi to 7 pi over 4, and back to pi over 4. All of these are exactly one distance away from each other. They're exactly pi over 2 away from each other. These are all 90-degree angles we're getting in there. You could think of it that way. So we really only need one starting point, that pi over 4, and we're not adding 2 pi over n, or sorry, 2 pi n. We're not even adding pi n and then doing that twice. Because all 4 of these angles are the same distance from each other, we can start with that pi over 4 and just have multiples of pi over 2, so that pi over 2 n. Now again, we could look at all 4 separately written out, but the goal is that we can start to recognize when we can have a little bit of a shortcut. And lastly, coming down to number 6. Number 6, we got to do some factoring, but we got to move this cosine first, so we subtract that cosine, factor a cosine out, and we end up in 2 different cases. We have either cosine is 0, and that happens where sine is 1, opposite from number 5, so that's at pi over 2 and 3 pi over 2, and then cosine of 1/2, which happens at pi over 3 and 5 pi over 3. Well, again, for writing the solutions, I see some shorthand we can do, because from pi over 2 down here, it's a distance of pi, and we do that again to get back. So we know x can be pi over 2 plus pi n. That encompasses both of these, and then every multiple as you kind of go around the unit circle. However, for the last 2, very similar to number 1 and 2 on this page, they're not some set distance from each other, so we got to view these and their multiples separately. So we're going to have x is either pi over 3 plus 2 pi n, fit it in there, or x is going to be 5 pi over 3 plus 2 pi n. So that kind of wraps up some of our basic skills with solving these, and we'll go on to the second page. Coming onto that second page, at the top, we're going to be dealing with equations that are quadratic in type, and quadratic in form. So what does that mean? Well, let's say look at number 8, one you're going to be doing on your own, we could really view a cosine of x as its own variable. And we saw some 5.1 and 5.2 as well. So this is really 2 times some value squared minus 5 times that same unknown plus 2 equals 0. Now, the methods we would solve this quadratic equation are the exact same methods we're going to use when solving this one with trig. So for number 8 and number 9, you guys will be doing that on your own, using exactly what we're going to do and model in number 7. So before we get started even on number 7, there's a tiny little detail to bring to your attention, and it's this guy right here. We're being asked to find all the solutions now from just 0 to 2 pi. So that's not having plus 2 pi n. This isn't minus 2 pi. This is finite. This is just the values that hold on the unit circle. So that's one thing to keep out on, especially on the homework and even more so in the midterm, is it just asking for all solutions or specifically solutions in some range? So let's get going on number 7. Number 7, again, if we treated it like something quadratic, we could say 2 times some value squared minus 3 times that value plus 1 is 0. And what would we do? We would factor that up. Now, it's not going to be just an x or just a y. It's going to be a sign. So it would have been 2 times y squared. If you need to write that off to the side and work it out that way, feel free to for now. For me, I'm going to keep it just with the trig. But this factors nicely for us as 2 times the sine of x minus 1 times sine of x minus 1. Now again, we factor in the quadratics in this sense, so we could set each of these equal to 0. So that means sine of x is going to give us 1/2 from this first, right? Because if this is equal to 0, you add the 1, divide by 2. Or sine of x equals 1. Now, again, we're always looking at the unit circle for this first half of 5.3. So on my unit circle, where is sine going to give me a positive 1/2? Well, that happens at pi over 6, and then again at 5 pi over 6. So that covers the 1/2 bit. And then where is sine positive 1? That only happens at one spot. That's straight up at pi over 2. So now comes writing that final solution. Instead of needing to find some tricks for shorthand or needing to encompass all those multiples, because we're locked into this 0 to 2 pi, right, this one rotation, we're only listing the values we find in that one rotation. So what are our answers? Our answers are pi over 6, pi over 2, and 5 pi over 6. So keep that in mind as you guys will pause in a minute after we do one more example. You'll be doing numbers 8 and number 9 up here. Number 8, really straightforward. We kind of already have it in a form to better and more easily see that factoring, and you'll approach it the same way. Again, keep it just in that unit circle. And for number 9, we're going to add a little spice from 5.1 in there, which you guys are totally ready for. So I'm going to have you guys do number 9 on your own as well. Number 9 has sine squared of x and a cosine x. But here's my hint to you before we factor. Get everything in terms of cosine. Now think to yourself from 5.1, 5.2, what do we like about sine squared of x? My hint to you is an identity. So give it a pause, give these two a shot. Coming back from you giving number 8 and 9 a shot. For number 8, really straightforward, right? This above quadratic, if you need to use that as a reference, factors into 2 cosine x minus 1, cosine x minus 2. Solve for each of those, right? We get cosine of x is 1/2, and that happens at pi over 3 and 5 pi over 3. And then cosine of x equal to 2, which hopefully felt familiar from the first page as this does not exist, right? Because cosine is going to be from -1 to 1. It can't be larger than that. So for number 8, our only two answers we have, because again, it's finite, it's only from 0 to 2 pi, is that pi over 3 and that 5 pi over 3. Now, looking at number 9, took a tiny bit of substitution. So hopefully you caught that sine squared, if I want everything to be a cosine, it's just a Pythagorean identity. So we could rewrite that as 1 minus cosine squared x. And now a little algebra, right? But everything's in terms of cosines. So we do a little distribution. We'll combine like terms, the -3 and the +1. And I personally don't like a negative leading coefficient. So I can write this out by flipping all the signs, right? Because I multiply everything through by -1. So now we got 2 cosine squared x minus 3 cosine x plus 1 is 0. And again, from there, if you need to, you can rewrite it like number 8 to factor it quadratically. And we end up with either cosine of x at 1/2, again, like number 8, at pi over 3 and 5 pi over 3, and cosine of x at 1, which happens at 0. It also happens at 2 pi. So take a minute. I'm for sure going to get in my pi over 3 and 5 pi over 3. And if you did or didn't even work that one out completely, think, should I be including 0, 2 pi, both? What should I be including to get that cosine of x equal to 1 included in this? Because we're finite, right? From 0 to 2 pi. Now, if you weren't sure, hopefully you kind of look back up to that interval. We include the 0 as our answer, and we go up to that 2 pi. So in this case, I'm not really looking at that 2 pi. I want to include the 0 as part of my answer. So now we got one more little strategy for how we solve some trig equations for the first half of 5.3. And that deals with converting things into being a quadratic type. So we spent so much of our math career in high school dealing with quadratic equations. The skills behind it are solid, and they're also really efficient. So we're going to try to implement that whenever we can. And number 10 is an example of how we do that. So if I have something, right, cosine on this side, sine on this side, it's not like number 9 where I had that nice identity to use quite yet. However, there is something I could do to kind of force that situation. And what is that? It's to square everything on both sides. Now, if I square the left, right, I can expand that. I get sine squared x plus 2 sine of x plus 1, which is nice. It's starting to look quadratic now. But what's even more important for us is the right-hand side turns into a cosine squared x. And we like that for the same exact reason from number 9. If I am going to deal with quadratics, I need all the same kind of variable, right? And for us, that unknown is this function. The nice thing about getting this cosine squared by itself is that is exactly the Pythagorean identity once again. So once we kind of have all of that now not only in quadratic form, but quadratic form for the purpose of really abusing that identity. We're going to use it a ton, right? Mentioned 5.1, 5.2, same here. Now everything is relatively a like term for us to get onto one side. So we'll move these over to the other side. We'll get 2 sine squared x plus 2 sine x equals 0. Those ones will cancel. We have a 2 sine x we can factor out now. And once again, we've taken something quadratic, factored it, so we can use that zero product property, aka we can solve each of those pieces equal to 0. So for this first equal to 0, sine of x will just equal 0, because we'll divide that 2 over. And then for the second half, we'll get sine of x is equal to -1 when we subtract that 1 over. So the trick here was different functions is kind of setting you off of, oh, I'm kind of stuck. Maybe I can use Pythagorean. Oh, bummer, not quite. And in that situation is when we square both sides to get it in that direction. And then again, you'll have your unit circle nearby, and we're asking ourselves, where is sine going to be equal to 0? Well, that's at cosine being either equal to 1 or -1. And then where is sine of x equal to -1? That's down here at 3 pi over 2. Now again, you might go, oh, but that's pi away, and that's nice because I can do shorthand. Once again, we're only working from 0 to 2 pi, so we only have to list those 3 values out. So now to wrap up the first part of 5.3, we have number 11. You guys are going to pause, give this one a shot. So kind of run through the few things, right? 2 different functions. So right away, that means I want to get everything in terms of one of them so I can solve for it, which means we want to use an identity, typically Pythagorean, but nothing squared. Well, we can always introduce that squaring, and that's what you'll do in number 11. My extra hint to you, if need be, is that we're ultimately going to be dealing with a final function of a cosine here, but we're first going to get it into a secant. So give it a pause. So coming up to wrap up number 11, I have most of it worked out. So again, leaving it off, we wanted to square both sides. When we do that, we get 1 plus 2 secant x plus secant x squared. Sorry, secant squared x. And that's equal to secant squared x minus 1. And what I'm doing here is I squared that tangent. Well, we know with a Pythagorean identity that tangent squared x is just secant squared x minus 1. Now, at this line, everything is kind of in a quadratic form, but we want to get it equal to 0. So as I pull everything over, my secant squareds are going to cancel out. And I boil down to the secant of x equals -1. Now we might come over here. We might have the unit circle. Now, majority of unit circles aren't going to have secant and cotangent and cosecant on them, but there's one more identity we can use. We know that secant is related to cosine. We know more specifically that 1 over cosine is secant, and 1 over secant brings us back to cosine. Well, this is kind of a rare trick kind of used in algebra, but if you ever needed to, and you have an equation, you can take the reciprocal of both sides, which means we could really take 1 and divide it by both sides. Well, that means we end up with a 1 over secant x equals 1 over -1. But we just said 1 over that secant x is cosine x, and 1 over -1 is -1. So that's how we get to just working with cosine in this problem. Now we go to unit circle if need be, right? Cosine is -1, happens only at one spot over here at pi. So the only solution to this original equation is that x is equal to pi. So that wraps up the first half of 5.3. I would absolutely have these notes handy as you work through that assignment, because if you don't know maybe that first approach to use, I would kind of relate back to which of these forms does it kind of fall in that we've seen, and then give that technique priority for solving it. So that wraps up our first half of 5.3. In our second half, we're going to see a few more techniques and kind of bring in our power of the inverse trig functions